This is the last topic, and then we go into the fun part, the last theoretical topic, I think. But I thought I should mention this because it's, I think it's relevant for any of you who want to use satellite data for the local scale. And I think if you work with sensor data or urban scale, then it could potentially be quite relevant. So the idea is to downscale satellite data, and the reason is, as you've seen, the resolution of this data is so coarse, right, that it's very difficult to get fine detailed information for peak level and so on. And so it's a very simple concept. We have two input data sets. One is our coarse resolution satellite data here, and the second one is some auxiliary data set, some helper data set that we have at fine level. So this doesn't have to be the same quantity as the satellite data. It can be anything. The only important thing is there has to be a correlation between these two input data, a spatial correlation. And as long as that is the case, we can use downscaling and get the satellite data at a higher spatial resolution. This is the same thing, but in a bit more complex manner. We have the input data from the satellite here, and then on the right-hand side, we have other input data sets. So for example, from a model, land use, or whatever you want, anything that is correlated with the input data set. And then the first step is you aggregate these to the same resolution and then calculate a linear regression model. And then you use the residuals from that model and do something called area to point tweaking. It's again a geostatistical method that I'm not going to go into, but that basically increases the spatial resolution, taking into account the autocorrelation in space. And in the end, then we use that, add it to a deterministic component from the model, and we get higher resolution satellite data at the output. So let me skip that and go directly to the more applied stuff. So this is simulated data. This is not real data. On the left-hand side, I simulated imagine the concentration field, like NO2, PM, doesn't matter. Just imagine anything. And then the true state of the atmosphere on the top left. So I call it the truth field. Right? We never know this in practice, but it's something to work with for developing this kind of algorithm. Now, the satellite sees only a very coarse resolution version of that truth. And that's the panel you see in the middle, right? So it has roughly the same shape, roughly the same patterns, but of course it misses out on a lot of the detail. But then what we do have is the thing on the right. So this could be a model, or it could be anything that is correlated with our original truth, but it's different quantities. So I'm not sure if you can see it, but this is, for example, values between 10 and 70, and here on the right is the truth, the left the truth is between 0 and 30. So it's completely different values, slightly different patterns. But the goal is that we combine the middle panel, the satellite data, with the right panel, which is our helper data set, and try to extract as much information as possible to get again the truth. We want to get to as close to the truth as possible. So if we do this downscaling, we basically combine these two as I just said. Now, validation then happens again against our truth. So we have like this sort of closed loop when we use simulated data. We cannot do that with real data because we never know the real truth anyway. But with simulated data, we can do this. So this is how this algorithm was developed. So again, we have a truth field here on the top left, and the satellite data in coarse resolution, our proxy at fine resolution. Now, as a reference, I basically show here on the lower left just what happens if you interpolate the satellite data without any extra information. Just just by linear interpolation, you get this very sort of smooth field that doesn't have much detail. Because it only uses the information from the top middle panel, right? But if you combine the satellite and the proxy data set and downscale them, you get the lower middle panel, down where it says downscale. And now compare that to the truth. So it's very, very close, right? And so this is in an ideal case what we want. In reality, it's never going to look as good, obviously, because it's a simulated example, but that's the idea. And what we can also do is we take this downscale panel on the middle and we aggregate it again to the spatial resolution of the satellite. And that is sort of a cross check, because if we do that, it should come again with the same exact value as what the satellite measures. So it's supposed to be what's called a math conservative approach. So the value shouldn't change. So that's the idea. And if you do this on simulated data, we see a definite improvement in the correlation. So on the left-hand side, it's just the satellite data. If we do, as a reference, just the bilinear interpolation, it's the center panel, we have an increase in R square, but not by much. But then if we use what's called here the Samira method, because that was a project, but it's the downscaling method, we get a much better correlation between the true value and the estimate. I'll skip this. So here's another visual example. This is the NO2 column for an area in the Netherlands, Belgium, and so on. It's very coarse resolution, as you can see. This is from an old satellite called the OMI, or relatively old instrument. So it can only measure very coarse spatial resolution. So this does not give us any or not much information about sort of the city level information. But if we then downscale it, we can get results like this. So this is the same exact quantity, the same units. This is still in column amount, so this is still not surface NO2, but you have much more spatial detail. You see the individual cities, you see the street, and so on. And this is because we use information from a proxy variable that gives us that spatial detail. Same example here, this is for northern Italy, the Po Valley, which is very typically also quite polluted. We have like a hotspot here in yellow over Milan, and then if you downscale it, we get something like this. So we have much more spatial detail. You can also see that the values for Milan are actually increased compared to the, let me go back to the previous one, because this is, of course, resolution is averaged over a relatively large area. But when you get finer resolution, you get also then higher levels overall. And yet, if you were to aggregate this back to the original resolution, you would get the original satellite data. So that's the beauty of it. Here's an example for AOD-PM. This is much more difficult than for NO2. It's still to some extent possible, but you don't have such a strong correlation between your model and your satellite data typically. This is for the Oslo area, downscaling. Here's another example for surface PM2.5 from MODIS, which is, by the way, something that we will calculate altogether later in the practical exercise. On the left is the surface PM2.5 from the satellite, and on the right-hand side, what you get if you take this, combine it with high-resolution proxy information and downscale that. So you have then really, I mean, you don't know this area, but those people who live in Oslo, they will basically realize the individual downtown Oslo area. We have Lillestrøm here, we have Drammen. These are like little satellite cities of Oslo. So this is the kind of information you can tease out. And I mean, of course, a lot of that information comes from the spatial proxy, but the values, they are all from the satellite. You can also then do the same thing as I showed previously for the Po Valley. Original data on top left, downscale on the top right. But now, in the meantime, we've gotten a new instrument in space that measures at higher resolution. So we can actually compare our downscaled result with two measurements, and that's what you see on the bottom left. This is high resolution NO2 columns from this performing instrument, and you can see relatively good correspondence. In particular, for example, this hotspot over Turin, which is not visible or nearly not visible in the original satellite image, is then visible in the higher resolution data. And obviously, what I do in practice now is I downscale this high resolution data set, but then I don't have anything to compare it against. So for this validation exercise, we have to do this. Some more steps about showing the improvement. I think we can skip that in the interest of time. Actually, no, I wanted to mention one thing. This downscaling works best if you do it on the surface NO2. And so I calculate the surface NO2 using a ratio. And this is the modeled surface to column ratio. And then you can apply this to the satellite data, and you get something called surface NO2 from the satellite data. And that you can then downscale, and this is what you see here. Again, the NO2 with a very small plume over the city of Oslo, and then the downscale plume here. I have a bunch of examples along these lines, which I go over a bit more quickly. Yeah, here's another example where basically the hotspot of the city of Oslo really only 2 pixels here, but then when you downscale, you get more information about where in these pixels, and you see still the original satellite pixels here in gray markers. You see where within these pixels we expect the highest concentration. So let me just jump over these in just a time, and then I'm nearly done. Oh, this is a nice one. I just want to mention that last one because you see also a plume here, and the plume in this case goes from the city towards the southwest, and then when you downscale it, you see how the plume is basically in this case mostly in the northern part of the spectrum here, and then when it's further down, it's sort of shifted towards the south. So you really can get a lot more information than you can get from the original satellite. So that was just the last part of the downscaling, and I think the downscaling is really nice in the sense that you get much closer to the spatial scale at which you have sensor data. And I know a lot of you work at the urban scale, so for that you really need sort of this urban scale information. So now I suggest that we start with this data use exercise. Originally I was planning to break before that, but I think now we are still all fresh enough, hopefully. So the idea is that we use something called the Google Earth Engine, and I hope most of you have signed up for this now. I've created a bit of code, very simple code, and I will explain this in a bit more detail. So the idea is that you just follow along. I've prepared 7 very small snippets, very small scripts that do different things. And Milos, can you help me to bring up the link again? I saw you had it earlier. Let's see. I guess we can. Actually, I'll share from my computer for the session. Okay, great. But now I get to Guys, did everybody get the link already or not yet? I'll put it back up. Everybody has downloaded a little text file from the link? Great. So this is a text file that contains a few code snippets, and you don't need to run this in Python or anything like this. We'll do this very simply. So those of you who signed up for Google Earth Engine, just open it now, and you should see something similar to this. Without code for now, it will just be an empty field. People are already running code. So this text file that you got, take the first snippet and paste it into this blank field that you see at the top, and it should look something like this. So it's just about 4 lines. Move it a little bit and then we'll mute. We are overusing Google Server. Okay, so guys, I want to explain a little bit what's going on here. So people are quite fast, so that's great. But I just want to tell you that this is like a hello world example, right? Just to show one data set. Basically, we've done the same thing earlier this morning already with just showing a simple data set. But here it's done with a bit of code, and this is JavaScript code, so it's not Python like we used yesterday. But I think it should be fairly understandable, I hope. So what I'm going to try to explain first, what's going on, and that is that we basically declare a variable. That's not really important. A variable called data set, and then we use something that's called an image collection. So an image collection, Google Earth Engine, is just a massive amount of images from one particular sensor. Sorry,
those libraries, Google produce libraries.
Yeah.
So we are now calling each and every function that they make the like filter date. Those are all functions that are built in for.
That's right. So this is the. I originally wanted to talk about Google Earth in the presentation, but we've already had too much presentation today. So, but yes, so Google Earth Engine is a cloud service from Google that allows you to work with satellite data in a simplified manner. You can go through this little website here, or if you prefer Python, you can also access it via Python, for example. But yes, all the functions that are on here, they're running on Google servers. So we're not doing anything locally. It's all ready to go. You should not have to import anything. What I wanted to explain is this thing called image collection. This is like, imagine you have like one big product. For example, Cassie mentioned Modis, AOD, right? That is one product, and an image collection is all images that have ever been taken worldwide for that one product, all times, all places, and so on. So that's a massive amount of data. What we're doing here is we're defining Copernicus S2, so this is Sentinel-2 surface reflectance. This is a very simple data set that is just a high resolution satellite image of the Earth. And then we use a function on that called filter date. So we basically just filter out all the images, still globally, all worldwide images between the 3rd of July this year and the 4th of July. So one day, 24 hours. And then we define a variable called visualization. You don't have to bother too much about this. It basically defines the minimum and maximum value that should be shown. But then the bands are important. So bands basically means, there was a question from this earlier, I guess. Bands is basically the wavelength that the satellite measures. So satellite can measure 10, 20, 30, 100 different segments within the electromagnetic spectrum, right? And so here we select 3 specific ones, and we select it for a reason because the channel combination 432, potential 2 means it's a true color image. So it's what you would see if you look down from space. P2 is always blue, wavelength roughly, 3 is green, and 4 is red, approximately. And so we do an RGB image with red, green, and blue. So this is the true color. Yeah. So far, so good? Okay. So then the next line basically sets the location of where we are in the hotel. I just looked up the latitude longitude for this hotel, and it sets the map it sends it on our hotel. And then in the last line of code, we basically add the median of our data set. And so this is a bit complicated because there's still a lot of images there, but sometimes they overlap. And so we just take the median of that data set. In this case, probably we only have one image per each location, so it's not so important. But later on, we will average over an entire month or longer. And then we really want to calculate the mean or the median of all these images. And so what you can do now, and I see a lot of you have done it already, you can just click run. And then basically these commands are sent to the Google servers, and up comes a simple image of our area that we are sitting in right now. So you can then zoom in. So you can see our hotel here. You can see the swimming pool across the street. When you zoom in a little bit, you can also, if you want, you can go to layers and then change the transparency a little bit. That makes it also a bit easier to see, because then you can see the base map through the satellite data. So this is just a very simple example. It has nothing to do with atmosphere or pollution. It's just how to bring in satellite data and visualize it. And what I want everybody to do now is to play with this code a little bit. I wrote 2 things in here. What happens if you pick a different date up here? So you see the filter date function up here. It has 2 days, 3rd to 4th of July. Change these a little bit. See what happens. Change them, for example, from 1st to 2nd, or change them for an entire month, for example, right? And see what happens. So for some days, if you have a short period, there will not be satellite data because this satellite passes only every 2 or 3 days. So So if you don't get any information, then it's like approximately. Yeah. So if you take, for example, a day before the one right now, probably there's no data for that, right? But at least now you see there's data for day or next. So in fact, I would recommend that you do out and you can see the right. It's again now doing a count and average median from the first of the line. And then multiply there and also the next one how we get the later on with data a little bit. Yeah. We have already two latest that's why we have the same layer price. You only need the so you don't need to make a copy of this thing that's right here. You can always copy it from this modify whatever you want. Don't be afraid to break it. So the other that goes back much further. Okay, great.
Tell them, tell them. Would it be worth?
Please take all the documents, everything for that file. Okay, that's what the person is. Then you can go
Not so much. That paper. It's just the, no, but I think it has to be. No, I received 2 years ago some paper for I think market or something like that. Some people in Japan remember something like that. One of them was Russian. I didn't know they use it. Some very silent. Yeah, I don't like that. But there are some people that are not in this area. They are very good. What about when Sonia we need to make rewrite at the moment it's just the every article that's what it is, just to tell one application I you see, and show you. I find that no. Then I wanted to make some, but I found it.
Okay, I think everybody's already moving on to the next scripts. So the point that I wanted to show, whoever hasn't loaded the script number 2 yet, you can do it now. And I already explained to the group over there, script 2 is basically exactly the same thing as before, only with a different band combination. This means we are using different parts of the electromagnetic spectrum. And you see here, the band combination earlier was 432, now it's 843. The two of the channels are still the same, they're just shifted over. But what we use now is this band 8, which is near infrared. And near infrared reflects very strongly in vegetation. So everything that you see here that's very red means it's a lot of healthy vegetation, very like dense forest, very green meadows and so on. And everything that's not red is, well, obviously something else. So you see, for example, fields that are plowed already, right? They appear more gray. So that was the point of this. Has everybody tried this already?
Yes.
Yeah. Great. Then we move on to script 3. You saw in the first 2 scripts that we had a lot of clouds. And so this is one of the problems with the satellites that we want to mask these out because they can really mess up your statistics if you do that. So this code is a bit more complicated, but it basically just reads a library that provides cloud or processes the Sentinel-2 data to be cloud free. And if you run this, you will see that, and you have to zoom out a little bit. You'll see that all the cloudy areas will not be cloudy anymore. They'll just be empty, right? They're transparent.
Yeah.
So they're masked out. So all the white pixels from the cloud are just taken out. And this is important if you want to do any kind of statistics or use this data. Doesn't work?
It's the yeah. No. It's not
So when you paste in the scripts, just replace the old one. Always have like one script at a time, and otherwise it gets
I don't just yes, but how? Yeah, how? And how it be structured? It should be structured. Yeah, and it can be structured to have a production of but just to see some production on the No, yes, yes, it is about 12. Well, yes, and one more I understand.
Does anybody get an error message for script 3 or does it work?
Yeah,
What error
Like
correct references. Yes. No, that is. Yeah, but I think where we are. Actually, what? It's but Philipp is going on vacation and she needs to respond to the messages and I'm going on the phone, so I will probably read my so but no, that as soon as possible.
You guys actually give
You wanted. We could do it to sacrifice.
We have tasted several different menus each other. You see only like you have like two layers except So this is very important if you use it for any of the not allow for you any processing because otherwise all participants get without the light. So that was show you that very best easy to do that. Not involved in getting rid of this stuff. Just running these two lines to script, it basically automatically does that for you. And now you can play around with this. Build everything that has a cloud capability of 50%. Now you can change this to 20%, 50%, and see it should be the area of cloud vary. 10% means or even something that considers me. The 40% the algorithm is absolutely equivalent to cloud. It will be a small. Okay, guys, I know a lot of you have worked already with this script number 4. The point in script number 4 is to show you air quality data. Previously, we've only looked at the Sentinel-2 data, it's just optical. Now we have actual air quality data. This is this two column that I showed previously. This is for a specific day, what like 3rd to 4th of July. And you can sort of play around with this, look how it changes in time, in space, where the high pollution levels also change again the dates, maybe just one day at a time, see how air quality changes then, and also make an average. Actually, we do that in the next script. Just change it by time. And then when you're ready with this, you can go to the script number 5. And that basically then calculates a monthly mean of the data set. So you see that in the script number 5, you have 1st of June to 30th of June, and we calculate the median of that. And by doing that, we don't have any gaps or barely any gaps anymore because we average a lot of different data sets on top of each other. Huh? POD.
Yeah, the PM.
Only in this industry, and again, to do a lot of average, I won't be a room because average out.
Mr. Schneider, look at this.
Yeah, it's really good. So that's how it is. That's how you need it.
No, that's not AUD,
That's Maya.
that's the PM. Oh, yeah, yes.
It's got the most idea. It's not the end. It's the IoT level. Then very last thing, we calculate on this. Very last. That's the next thing.
After this, I think that the website.
Take too long to calculate, but
All this variable on this line calculates the ratio every point in the range between sorry, the circle divided by the formula, right? And we multiply it times the A of these. So the A of these is so you only have a I was going to explain this to you. Because it's a lot of money. Yes, probably a couple of terabytes. Everyone here?
If I don't think that the data and some averaging on which I think we're not measuring out correctly or something. I don't think that's right. I think it's not. I just looked into the another where you have the
It's just for
but no, not from Moodle.
well, I mean the modus here that we look over India, that was really bad. It had like these rectangular squares in the middle of India. I remember that. It should be the so there is something wrong with the product, but it didn't look that bad.
Now I think these drives are I don't know what they do.
One okay here? Let's stop. So basically, that's just so that and you can play around a little bit. If it's possible, make sure sometimes that takes a long time, like too many new converts the different units, the different units are in one. It converts it into the number of molecules present with that traditional unit. This unit converter, and then it will be multiplying the rate of you can units are 10 to the 15 molecules. Imagine all molecules. And that's the rate. Remember that the satellite only costs usually around midnight. So if you do a time period of 1 week, and we will average it at 47. Always 40 at noon. And if you do a year, you do about 50. Like they're not average because we have a median. But no, here in this case we have median. But it's going to be next one. You come to whatever number that you have, and then you apply and do this unit for and the rest is just
Okay, guys, many groups have already moved on to the AFD stuff. What we do here is basically we don't look at NO2 anymore. We look at aerosol optical depth. And the first script, like the script number 6, it just shows aerosol optical depth for MODIS for 1 day. This is for 29th to 30th of June this year. And you can look a little bit on how the data looks like, where we have high values, there are low values. You can try to produce a month-long average, for example. And when you're familiar with this AOD data set, then you can move on to the very last script. That's number 7. And this I have to explain in a bit more detail because there's a lot going on in that script. Has everybody already looked at the script 6 with the AOD? Yes. Okay, let me do the last one for today. And that I will explain a little bit because that is the most complex one. Okay, so what happens in the script number 7? So the goal here is the satellite uses only the AOD, right? But what we really want is not this vertically integrated value. We want the PM at the surface, right? And in order to do that, we need the help of the model. And because the model can give us roughly the ratio between the AOD and the surface PM 2.5. And this is what we are trying to do here. So the first 2 lines just define our start and end date, like before, second to third line. And in the next, we define a data set. And this is now not a satellite data set, but it's a model. But this is from an institute in the UK called ECMWF. And it's a Copernicus service called CAMS that provides operational modeling. And then we're using the near real-time version of that data. So we define this collection, and then we filter by the start and end date. And then in the next line, we basically get the model AOD for this particular time period that we define on top, right? So we select the total aerosol optical depth at 550 nanometers. This is the variable number. We calculate the mean because this comes at a few hours intervals. And we do the same thing for the model PM2.5. Now, at this point, we could, of course, just use the model PM2.5, right, and just get rid of the satellite entirely. But we know that the model has huge problems with calculating this properly, especially on the global scale. So we trust more the satellite AOD, but in order to convert it, we trust basically the ratio between the model AOD and PM. And this is what we do in this next line, where we go the surface to AOD ratio is just the PM2.5 from the model divided by the AOD from the model. It's just a simple division. And then we take this ratio and we multiply it with our satellite AOD. And if you, I should show an equation of this. If you can imagine this, you have microgram per cubic meter divided by AOD times AOD. The AOD divides those out of the equation, and all we have left is the microgram per cubic meter. And that's exactly what we do. This is a really poor man's method of doing this, but it's a simple way of showing you in principle how this would work. And this is what we're doing. Well, no, here we basically obtain the MODIS data, like in the script 6. We define the image collection, we select our data set, filter by start and end date, take the mean for this start and end date, and then multiply by 0.01 because they have some scaling factor of 1000, not important. But then the real magic happens in this one line afterwards, where we say, okay, the MODIS derived PM2.5 is just the MODIS AOD multiplied with the ratio we calculated from the model. And then we just rename that data set to PM2.5. And the rest is then this visualization. We have 2 things here. We visualize 2 layers. One is the AOD from MODIS. The second one is the PM2.5 that we just derived. Let me just run it. So because we now visualize 2 layers, you have to go here to this layer button and you can select the 2 to better understand what's going on. So let's look first at the aerosol optical depth. So we deselect the first layer. So this is what the original MODIS data set looks like, an aerosol optical depth. And there's a lot of architects that are discussing that with Keston, but ignore those for now. But then basically when you switch your layers from aerosol optical depth to motor surface PM, you get the same thing in terms of spatial patterns, but you get different values. You can see this if you click here on the top right, you see a thing called inspector. Click on that one, and then you can click anywhere in the map, and it will give you the values for both layers. So it might take a little while, but here you see it now. So for example, we have an optical depth of 0.06, and from that, the algorithm calculated PM 2.5 of 3 microgram per cubic meter, approximately. This is most likely very wrong, but as I said, it's a very poor mathematical. And you can do the same thing. You click on more extreme values, like in a hotspot. So there we have an aerosol optic depth of 0.6, and that would translate approximately into a PM 2.5 concentration of 41 microgram per cubic meter. Does that work, the hospital with layers? Because when both layers are active, they are both active by default, and it's a bit difficult to see what it's about. So I recommend you to turn one off and only look at one at a time. Yeah, so here's the values. That's crazy.
Okay, that's nice. So I know we're going to take it to this is one of us.
In general, these are pretty much But be careful not to be Okay. Very bad.
the headline. There are senses but they are used information in the but there's no information coming from because then you will there is the they have a it's okay. Because then you have the fixed values. It's quite convenient, but then you have all these collections of data which they have with specific quality values, which are the recommended ones, but then they might also be replicated on the latest data. So I think it's very good. I think I'm probably yeah, no, it's good. But the aerosol is so much more complicated than I worked with, I did my PhD with laser and then we looked at structure. It'd be nice. Are also going into the coding. He didn't. Normally, it's very low. It was yeah, quite yeah, we have and especially this political that's really nice because all the all the information in the spreadsheet between the 30 kilometers, and then see that we see the good tree. But now, I like fine. And that's where last time they had this of it. They did, I remember, affection picture, we marked them. And sometimes it can be also because they had a study on the pools now in the ship with the roads in the Africa. On their own. So, yeah. Anyway, please. It's on the side. Did you send me just where I can find I think I can send I hope yes. Ship. Here. Yeah, if you get actually this file I complete there are not so many like that. Counting about only few. I know that you they are for some that is coming in that harbor of block pocket. There is lot of there is
Very complicated.
Guys, one more thing before we finish. I think several people ask me, what if I want to show some other variables and so on? If you want to do that in Google Earth Engine, you go to something called the Earth Engine Data Catalog. And here you basically have a list of all the various data sets that are available. It's a huge list, very comprehensive. Let's say, for example, you want to look at, go again to Sentinel 5P. Sentinel, for Sentinel 5P 2.8 gives some information about which variables are available from that satellite. So, for example, aerosol index, cloud, carbon monoxide, formaldehyde, nitrogen dioxide. We looked at this one quite a bit. Ozone, for example, and yes, sulfur dioxide, methane. So let's say you are interested in methane. We would, correct?
How old is the big?
It's how? What do you mean? How old is it? So it says here data set availability from 2019 to present. This varies for all the different data sets. Some of them start already in the 1990s or so, and many start more recently. So then you click on it, and then you get a description. So this is what you just asked about, availability of the data. So from 2019 February to 2022 July 5th. So basically now, where it comes from. Here it gives information what you need to enter in the very first line, or not the first line, but some people ask about, hey, how do I know the string that I need to enter to get the specific product? This is the one that you want to use here for methane. And then below that, it gives you a description of the data set, like where it comes from, what retrieval algorithm was used, how it was processed before it was ingested in Google Earth Engine. And then at the very bottom, I think this is one of the nice things, they have little examples. So if you want to explore this, you don't even have to program anything yourself. You can just sort of open this piece of code, this little example in the code editor, you just click on it, and it will open this particular thing, and you can immediately then run it, and it will show you some examples in this case for the methane product, see where they yeah, so it loads a global map of methane concentration from Sentinel 5P for what is this, like 1.5 month period. And so this is a nice way of playing with the data. You just look at this data set directory that I just showed. You just find it by the Earth Engine data catalog or whatever, and you get there. And then you can just browse through the various satellite data sets, various products. And if there's one that you're interested in, go to the bottom of the page and you find an example script that you can then immediately load and play around with it and do exactly the same thing that we just did, change some of the times, maybe the names of the variables that you want to display or anything else you want. So I think that will be a nice thing to explore. You can even search that. Let's say we're interested in, I don't know, aerosol, for example. The keyword, you get all the various data sets that are related to the aerosol. So you can do that as a homework tonight, over the weekend. But unless there's any other questions, I think we can finish here then. Yeah, I hope it was useful in some way to learn a little bit about the satellite world. And I really hope that some of you have sort of gotten a little motivation to try it out in the future with some of your own studies. And if you do, then just don't hesitate to send me an email. I'm happy to help with anything. So, no problem. Yeah, I kept as well, of course. So just send us an email, and yeah, it would be nice if some of you.
Thank you. Yeah, but don't go. I think Milena wants to. Yes. You're not free yet. Sorry. Moment.